All right, here we have lesson 1.03, graphing linear functions. I'm going to go ahead and skip to these skills and keywords. So prior to this, make sure that you kind of review plotting points, slope, slope-intercept form, and point-slope form from Algebra 1. Here we have a parent function. That is the most basic form of a function, and it can be transformed to create a family of functions. A linear function we have is a function with a constant rate of change called slope. So rate of change and slope are going to be used interchangeably throughout this lesson. The graph is a line, and the parent linear function is y equals x. Key features of a linear function, there are several embedded through here, but we have domain, range, and behavior. Zero, root, solution, x-intercept, those are all interchangeable. Those all mean the same thing. Y-intercept and rate of change. We also have the inverse of a function, which is noted as f to the negative 1 of x. And these equations have inverse operations in reverse order. And so you would simply solve this for f of x and rewrite the equation that way. The x and y values are switched from the regular function to the inverse, and the graph of the inverse is the original graph reflected over the line y equals x. So again, the inputs and outputs are switched. And then transformations of a function, there are several there. Make sure that you click through these on your own time if you don't recall them from Algebra 1. Getting into average rate of change, that's a fancy name for slope. So average rate of change measures how the output value or the dependent variable changes in relation to the input. Your average rate of change function is calculated over an interval. So inequality notation from A to B, this is the interval between the x values. Interval notation is square bracket A, comma, B, square bracket. Interval notation, which you will see throughout this course, uses parentheses for values that are not included in the interval and brackets for values that are included in the interval. This interval is between the x values A and B, including both of those values. So 2 coordinate points, you may be given 2 points, a table of values, or a graph. To calculate the average rate of change of a function, we use our slope formula, or this expression, f of b minus f of a over b minus a. That is the same thing as y1 minus y2 over x1 minus x2, where a and f of a and b and f of b are the 2 points of the function. So again, using the slope formula, just kind of written slightly differently, in different form. There are a few examples here. If you do not understand it after we go through the guided examples, please make sure that you click through these examples and read them. So finding the average rate of change of f of x over the interval 0 to 2. To find the average rate of change, you need the two inputs and their outputs. So if a is equal to 0, then f of a is the same as f of 0. So we are going to look for 0 on our x-axis, which is here, and we will find the y coordinate of 4. If b is equal to 2, then f of b is equal to f of 2. So f of 2, we'll look for 2 on the x-axis and go down to our line where it meets, and that is at negative 2. And I'll go ahead and submit that first. And then average rate of change. So do not type this in. I'm going to just show you the math here. So average rate of change, we have 4 minus negative 2 over our x values, so 0 minus 2, which then gives us 4 minus a negative 2, gives us a positive 6, divided by 0 minus 2 is negative 2. And 6 divided by negative 2 is negative 3. Now, it's probably hard to see, but I'll try to do it in Desmos. Shrink this down. There we go. So again, we have our outputs 4 minus negative 2 over 0 minus 2. And then Desmos will actually just kind of do it for you without having to simplify. All right, moving on to parent linear function and its key features. So function families come in different shapes. For example, what is the difference between x squared and 2 to the x? They both have an x and a 2. They both equal 4 when x is 2, but eventually one becomes bigger than the other. There we have a quadratic versus an exponential. And so just like people in a family share similar traits, functions in the same family share similar shapes, behaviors, and rules. So we have our linear parent function is what we're going to start with. And again, that is in the form of f of x is equal to x or y equals x. Linear parent function is also known as the identity function. It is called the identity function because each output value is the same as the input value. So in this case, if we put in 0, we get out 0. If we put in 3, we get out 3. Each type of function has its key features. The key features of a linear parent function are your x and y intercepts. The x-intercept is where the line crosses the x-axis, and the y-intercept is where the line crosses the y-axis. For the linear parent function, the x-intercept is at 0, 0. The y-intercept is at 0, 0. Now, if we add in a constant or a slope, those numbers change. Domain and range. The domain is the domain of a graph is the set of all possible x values or inputs spanning from left to right, while the range is the set of all possible y values or outputs spanning from lowest to highest. These are typically expressed in interval notation. For a linear parent function, our domain is negative infinity to positive infinity. We also, since it's infinity, it's not a definitive number, so we use parentheses instead of brackets. And then the range is the same. End behavior. So end behavior of the linear parent function describes where it goes off to. So in this case, our linear parent function is positive. So as x goes to the left, the line is going down. As x moves to the right, the line is going up. And so this is read as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches positive infinity. Again, looking at this graph, as we move to the left of our graph, move to the left as x approaches negative infinity, our graph is going down. As we move to the right or positive infinity, our graph goes up to positive infinity. That is end behavior. Intervals of increase and decrease. A function is increasing when the x values and function values are both increasing. So a function is decreasing when the x values are increasing and the function values are decreasing. All intervals are written in interval notation in terms of x values. So for the linear parent function interval of increase, we have from negative infinity to positive infinity. Intervals of decrease, since our graph is always increasing, the interval of decrease does not exist, and so we would write in D and E capitalized. Intervals of positive and negative describe where the function is above or below the x-axis. A function is positive when the function values are above the x-axis. It is negative when the function values are below the x-axis. All intervals are written in interval notation in terms of x values. So x-intercepts are neither positive nor negative because their value is 0. For the linear parent function, we have an interval of positive from 0 to infinity. So from here up to infinity. And again, the intercept is at 0. So that is not included, and hence why there's not a square bracket there. And then interval of negative, our values are below the x-axis from negative infinity up to that 0. And again, this is read from left to right. So it's not 0 to negative infinity. Negative infinity is below 0. And then average rate of change. In linear functions, the average rate of change is constant. That is your slope. It is the same at any interval of the function. You can select any 2 points on the line, and the average rate of change will be the same. For the linear parent function, our average rate of change is 1. Again, these are the key features of the linear parent function. These key features change when the parent function is transformed. Let's look at some of those transformations. So the equation of a transformed linear parent function is in the form of f of x is equal to a f of x minus h plus k. So the values of a, h, and k each change the graph in a specific way. So let's look at what they do. The value of a is either a vertical stretch or compression and can also be a reflection over the x-axis. So if the absolute value of this first number is greater than 1, your graph is stretched vertically, meaning that the graph is taller or narrower. If the absolute value, so taking out that negative, if that a value is between 0 and 1, so typically a fraction, the graph is compressed vertically, so the graph is shorter or wider. The sign of a, so positive or negative, if it's negative, the graph is reflected over the x-axis. So for example, we have f of x is equal to 2x, that is a vertical stretch by a factor of 2. 3/4 x is a vertical compression by a factor of 3/4. And then -9 is a vertical stretch by a factor of 9, but also a reflection over the x-axis. That negative just indicates that it is a reflection. Horizontal shift. This is kind of backwards from what you typically think because this minus in our formula. So if a constant h is added or subtracted to the input value x, the graph is shifted horizontally. So a horizontal shift occurs inside the parentheses of this function. If h is less than 0, the graph shifts left. If h is greater than 0, the graph shifts to the right. So pay close attention. This is the opposite of what you think may happen at first. So if we have x minus 6, the value of h actually is 6, so the graph shifts to the right 6. Plus 8, if you rewrite the function with the minus, we have minus -8, so the value of h is actually negative, and so the value will shift the graph to the left. So again, it does the opposite of what you typically think it might do at first. So -6 will actually shift it to the right, plus 8 will actually shift it to the left. Vertical shift does what you think it normally does, so adding a k value will shift the graph up. Subtracting a k value will shift the graph down. So x plus 3 will shift it up 3, and then the x minus 6 shifts it down 6. And this happens outside of those parentheses. Again, a couple of examples to look through if you need that additional practice. So write the linear equation with the following transformations. A vertical stretch by a factor of 7, so that gives us our a value of 7. A horizontal shift left 3. So that would look like x plus 3 in the parentheses. However, if you put that minus in from the formula, that actually makes our h value negative. And then our k value, vertical shift down 6, is going to be a -6. And then rewriting that function with those values in there, we will put the 7 here, the -3 here in parentheses, and then the -6 here. Simplifying that, that looks like 7x. X minus a negative becomes plus 3, and this plus minus 6 will become just -6. Graphing transformations of a parent function. So again, the slope-intercept form of a function is y equals mx plus b, where slope is m, and b is the y-intercept, which is also the k value of the transform function. Point slope form is y minus y1 is equal to m times x minus x1, where x1 and y1 is a specific point on the graph and m is the slope of the line. An equation in point slope form can be rearranged to solve for y, therefore writing it as slope intercept form. Again, here are all of your shifts. So a horizontal shift to the right looks like x minus h. Horizontal shift to the left looks like x plus h. Vertical stretch, a is greater than 1. Vertical compression, a is less than 1 but greater than 0. Reflection over the y-axis gives you that x-axis. Reflection over the x-axis is when that a value is negative. Vertical shift up is when there's a constant added to the end of our function. And then vertical shift down, constant subtracted to the end of our function. We have a built-in graph should you need to use it. I always recommend checking your work with the graphing calculator. So I'm going to skip down to guided example 1. Graph the linear function with the following transformations: a vertical stretch by a factor of 2, and a reflection over the x-axis is going to be -2 as our a value. Horizontal shift right 3, we have a value of 3, and a vertical shift up 1 is a k value of 1. So write the equation of the transformed linear parent function in the form of f of x is equal to a times f of x minus h plus k. So what that's going to look like is we have a value is -2, and then I'm going to put the parentheses, x minus, because remember there's a minus in this formula here, and then our h value is 3. And then our k value is +1. Then I'm going to write the equation in point slope form by simply moving this. So in point slope form, this part stays the same, but this +1 is actually going to move to the left side of my equation. So remember, point slope form is y minus y1. So when I get rid of this +1, I would subtract it to this side, and then is equal to m, which is the slope, and x minus x1. So you can take and copy this first part down here to the right side of our equal sign, and then we're just subtracting that 1 to this side and writing it in terms of y. Start with any 2 points from the linear parent function. Again, you can check this with your graph, but we are going to start with -1, -1, and 4, 4, and use our transformation. So we know that the value of h is 3, so the function is shifted to the right 3. So we're going to use the coordinates of the parent function and add 3 to each of the x values. So -1 plus 3 is a +2. And we'll bring down the y values. Same thing for the second point. We're going to add 3 to the x value, so 4 plus 3 is 7, and we'll bring down the y value. Then transforming our points from up top, so the 2, -1, and 7, 4, we have an absolute value of 2 as our a value, which means that it is a vertical stretch. Using the horizontally shifted coordinates, these ones here, we're going to multiply each of the y values by 2. So leave the x's alone. -1 times 2 is -2. Make sure you do not include any spaces in your answers or it will mark it as incorrect. And then bring down our 7, and 4 times 2 is 8. The value of a is negative, so the function is reflected over the x-axis. In a reflection over the x-axis, the x-coordinate stays the same and the y-coordinate changes the sign. So use our vertically stretched coordinates, these ones, and change the sign of the y values. So we'll leave the x's alone. -2 becomes a +2. and 8 becomes a negative 8. Reflecting it over the x-axis changes the sign on the y's. Last but not least, we had a vertical shift up 1, so that applies to your y value. So we're going to simply add 1 to each of the y values. So again, the x's stay the same. 2 plus 1 is 3. X stays the same. Negative 8 plus 1, be careful, is negative 7. Does not become negative 9. That would be negative 8 minus 1. All right, write the linear equation in slope-intercept form with the following transformations. We have a reflection over the x-axis, a vertical compression of 1/3, and a vertical shift down 5. So our vertical compression and reflection both affect our a value, or our slope. And so a compression of 1/3 and a reflection over the x-axis looks like negative 1/3 as our slope, or a value. Remember that k is the same as the y-intercept, or b, in our slope-intercept form, and a vertical shift down 5 would be negative 5. And then writing the equation of the transformed linear function in slope-intercept form, that is your y equals mx plus b. So I'm going to start with y equals. M is the negative 1/3 x plus b, which is just negative 5, or minus 5. Next up, we have inverse of a function. So hopefully by now you are familiar with the term inverse. Multiplication and division are inverses of each other, same thing as addition and subtraction, and square and square root. So for example, if we have the set of coordinates 6, negative 1, the inverse of that is swapping the coordinates. So you're going to switch the x and y values. The points S are reflected over the line y equals x to graph the inverse of function S. All inverses have this property. So if you fold the graph along the line y equals x, each point on S and its corresponding point on the inverse match up. We'll skip down here. So find the inverse of g of x is equal to negative 1/2 x plus 5/2 algebraically. So we're going to replace the g of x with y to start with. And then in our equation, we swap the x and y. And then we solve the equation for y. So in solving this, since both of our fractions have a 2 as the denominator, we can multiply both sides of our equation by 2. So here they multiplied this by 2, the x by 2, and then this by 2, and we're going to simplify. So 2 times negative 1/2 is just negative 1, but we're going to leave off the 1 and just put y. And then 2 times 5/2, the 2's will cancel out, and this is just plus 5. Solve for y and write the inverse in slope-intercept form. So here's my calculator. We have 2x is equal to negative y plus 5. So your first step in this is to swap the, we've already swapped the x and y values. We are going to actually solve for y. So to isolate this y over here, I can take and add 5 to both sides. Subtract 5 to both sides. 2x minus 5 equals negative y, and then divide everything by a negative. So I get negative 2x plus 5 is equal to y. And that is what is our inverse in slope-intercept form. So negative 2x plus 5. Graph the inverse of the function 3x minus 8, choosing 2 points on g of x. We have 3, 1, and 5, 7, the coordinates of the inverse function. So if just using the coordinates, we will go ahead and flip them. So 3, 1 becomes 1, 3, and 5, 7 becomes 7, 5. And then you can always verify using the graph. Moving on to the real-world applications part of things. Again, there's some examples there, but we are going to try to jump ahead to save time. Michelle rides her bike for 3 hours and is 35 miles from her house. That is our output when x is 3. After riding for 10 hours, she is 112 miles away. What is Michelle's average rate of change in miles per hour? So that's just setting up our inputs and outputs. They give you the equation down here. So 112 minus 35 is actually 77. And 10 minus 3 is 7. 77 divided by 7 reduces to 11 miles per hour. And that's her rate of change. There we go. Using 3 and 35 and the average rate of change to write a linear equation in point slope form that models the distance y in terms of x. So again, point slope form looks like y minus y1, which is 35, equal to the average rate of change, which is 11, our slope, x minus x1, which in this case is 3. And that is our equation in point slope form. Computer's slowing down. All right, Anne receives a monthly base salary of 6% commission. Before I read the rest of this, Anne gets 6% commission on each shade. So the average rate of change as a decimal is 0.06. She made $2,500 when she sold 200 shades. That is our point 200, 2,500. Using the given point and the average rate of change, write an equation in point slope form. So y minus 2,500, make sure you include the comma, is equal to 0.06, and our x value is 200. And so that is our equation in point slope form. And that is it for this lesson. There is a summary page. Make sure that you click through if you still need additional assistance in this lesson.